Hello and welcome back for another season of the Oxford Online Maths Club. My name is James, I work here at the University of Oxford, and this is the Online Maths Club where we talk about supercurricular maths, extra stuff that you probably not learning in school in the classroom if you're doing a school system like A-levels or IB or something like that. If you're not doing A-levels or IB or anything else like that, you're still welcome. These are on YouTube for everybody, they're recorded and you can watch them back afterwards. You can even watch them in slow motion or in double speed if you want to. While we're running this live, we've got people live in chat. I can see Jamie is here and Erin is here, and hi to Oscar as well. If you want to join us, we're on VVox. We've got some complicated code. I'll read it out at the start of the season here. It's 100376708. So there you go. It's also on the screen at the bottom down there, and I can see people joining now. Hi to Seb as well. Great to see names I recognise from last season as well. It feels like it's been a really long time. It's been actually only 3 weeks since season 5. But you know, 3 weeks can feel like a very long time. I can't actually remember how to do a live stream after 3 weeks, so I imagine I'm going to make loads of hilarious errors. Hello to Nicholas and somebody's, I don't know if this is Johnny in the third person or somebody's friend Johnny is here watching separately, so hi to Johnny in the third person. Brilliant stuff. We're going to get this together. The idea here is that we're going to do extra bits of maths. Some of you might be required to write some sort of personal statement, some of you might be required to write some sort of EPQ essay sort of thing. But even if you're not, you might like to see some other bits of maths. Hi to it was Johnny as well, but you're being okay. You are Johnny, right? Cool, good. Sorted out that identity crisis, so we're good. You might have noticed on screen I've got an advert. This is slightly unusual. I've got an advert for the thing you're currently watching. So I guess it's sort of worked. Self-fulfilling almost. This is Oxford Online Maths Club Season 6. It's supercurricular mathematics, maths from beyond the curriculum. We're going to be doing this each Thursday, and I think the thing I wanted to let you know is that we're running it for an hour and a half. So we're making each stream a little bit longer than last term, but we are stopping a little bit earlier. We're stopping 1st of June. So we're going to do 6 or 7 episodes like this. So 6 or 7 episodes like this. So, but with an extra half an hour. So you do the maths. That is slightly less maths club than last season, but it's going to be even more fun than ever before. That sounds like a claim that I can be held to, so let's be really careful with this. I've also got an advert on screen for the Mat live stream. It starts the week after this, and it's starting a little bit earlier than normal. You can maybe see how we've decided to start Mat live stream a bit earlier and stop the Maths Club a little bit earlier, so sorry about that, I suppose. But also, if you look back at the old episodes towards the end of season 4 and towards the end of season 2, some of those are just me, and they're not the best episodes. I shouldn't say that because today is just me. Right, good. I would like to know how your day was today. I think yes, I would. For new viewers, we do this at the start of each live stream. I would like to know how your day's going on a scale from 1 star to 5 stars, with 5 stars being the best. And it's always interesting to me seeing what the first few votes are, because those are people who've got the VVox app open. They've been through all of that waffling introductory chat. They've been waiting for their chance to vote. So those are people who are very keen on voting. If you want to join in, that's happening over on the VVox right now. They are longer episodes, and I promise that the length is not just me rambling at the start. I'm doing a bit of rambling because I want to get everyone on board for the episode, but we might also try and fit more maths in if we're lucky. Herbs just had their last mock exam, and it was today. Which one was it, Herb, and how did it go? I just guess we don't know yet, and also mock exams, so it's just for pretend, right? Never really understood that word. It's sort of like, mock's got this kind of double meaning. Look at this chart! Look at this chart! That's lovely! It's like Benford's law, but backwards. Benford's law is the thing about numbers in news reports tend to start with 1 more than 10% of the time. But this is backwards because look, it's this lovely distribution of 5, 4, 3, 2, 1. I'm always looking out for people who vote for 1 star or 2 stars, people who are not having a great day, people who are having a rubbish day. I was having one of those. It was not a good morning. And then the sun came out, and now over in Oxford it is absolutely lovely. So I think my day is up to at least 3 stars, but you know, possibly even 4. We'll see. I'm going to explain a tree today. We'll see. I'm trying to make sure it's one of the episodes that's good, not one of the episodes that's a bit weird, but you just never know. You just never know. Herb says the exam was physics, so but we'll take it. Right, I need to press that to go back to. There you go. Herb talking about physics on screen. Recorded for all time. You can also thumbs up people's comments in chat. That doesn't do very much, except, you know, give them a warm fuzzy feeling to see that they've received a thumbs up from somebody else out there who's tuning into a maths club. But you know, I think at the end we can look at who's got the most thumbs ups, but it's really not a competition. It's raining where Niklaus is. And you see, that's something where I would like to give a down thumbs up, but I haven't enabled those because I was scared that people would misuse them. Yeah, so south, Oxford's quite south. That's one of those days that feels quite south, and sometimes it feels not so south. Anyway, right, math club. Let's talk about a tree. Is that all right? Can we go? Are we happy? We've got a lot of 4 and 5 stars in the voting. Oh, physics is the comment about physics has now got so many like warm fuzzy feeling for Herb. Brilliant. That is the sort of voting we like. My plan for this is I want to show you a tree. I want to tell you some standard things about the tree. I want to tell you something that I sort of spotted that I couldn't prove, and I had to go and look it up, and I had to go and look up somebody else proving it, and somebody else explaining it. What I want to do, if I've got time, is I want to try and show you what that's like of looking something up and looking at other people's mathematics and trying to extract the information that you want. Because I don't think I've ever seen anyone do that before. If you're aware on YouTube of somebody going through the experience of how they learnt mathematics, maybe some sort of study blog or video or something, then that sounds pretty cool. But I'm going to have a go at doing that sort of content. But I'll do normal stuff first, where I just like show you some maths and talk about it. Because I think that's more reassuring if I'm telling you about maths, rather than saying, I didn't know this, and then I looked it up and I found something slightly different. Okay. As always, if you've seen this before, then be happy and chill. Let's not try it. No spoilers. So the tree I want to show you is called the Calkin-Wilf tree, which is a pretty cool name. It is named after 2 people, Neil and Herbert S. And as is usual in maths, there's a little bit of debate about whether the people whose names are on it, whether they were literally the first people to ever think about this tree, or whether some other people thought about versions of it first. This is one of those cases where other people thought about versions of this first, but their account of this tree was sort of so good that the names stuck with their names on it. Neil Calkin and Herbert S. Wilf are both combinatorics sort of mathematicians working in the US, although Neil studied in the UK for a bit. Okay, so the combinatorics people. Herbert's, I guess one of the bizarre sort of coincidences in this world or something is that one of Herbert's PhD students was Richard Garfield, PhD, who's the inventor of the card game Magic the Gathering. So there's sort of like this weird, vague celebrity link that this is the PhD supervisor of somebody nerdy enough to invent a very, very nerdy card game. There's a very technical question about CIE board A-level maths. I have no idea what's going on there, sorry. Anyway, right, let me show you the tree. So, it's a tree made of fractions, and it works like this. The fraction 1/1 is at the top of the tree, and underneath each element in the tree, there are 2 children. I'll show you the rule in a second. There are 2 children underneath. The rule for the children underneath each element in the Calkin-Wilf tree is that if the fraction up here is a over b, the ones underneath are a over a plus b and a plus b over b. That's the rule for what's underneath what in the Calkin-Wilf tree. Okay, so I'll say that again, sorry. For each number in the tree, starting with 1/1, the things underneath are the same numerator over here on the left and this one on the right's got the same denominator as the thing above, and then the other thing is the sum of those two numbers. You're supposed to write these things in lowest terms, but it doesn't really matter. Things tend to stay in lowest terms if you started in lowest terms, so that's all right. Let's work out a few more things in the Calkin-Wilf tree. I think it's called a tree, I suppose, because it's like these sort of binary branching things that if you drew it the other way up, it might look like the branches of a tree or something. It's a kind of maths word, I guess. I find it easier to write in the numerator and the denominators first and then put in the sum. So here I write the 1 over here, the 2 over here, and I do 1 plus 2 is 3. Welcome to the Oxford Online Maths Club. And over here, 2 over 1, 2 plus 1 is 3. So you write those numbers in there as well. Okay, Calkin-Wilf tree going pretty well so far. We've got some fractions in here. In a moment, I'm going to ask you if you can see any patterns or see anything happening. To which I think the answer should be yes, I can see at least one thing happening, but who knows? Live stream does involve some audience participation, so we'll see how that goes. Oh, Nicholas is doing it for me, thank you. Sadly, due to chat lag, by the time I saw your message in chat, I'd already put things on the board. Yeah, I think I agree with your numbers, so let's have a quick look. 1 over 3, 3 over 2, 2 over 3, 3 over 1. Yeah, cool, right, applying a rule, good. We got more and more fractions. I think nothing is too obvious at this stage. I want to make sure we're on the same page of how this works, because I want to talk about properties of this and talk, maybe even prove that it does certain things. But I want to check that we understand what's going on. Swap over. So Nicholas is asking about a swap over. What swap over? What do you mean? What do you mean by swapping? So this is a little bit like start of season 5. I showed you Pascal's triangle, and we played a game for a bit of what patterns can you see? Can you see anything you recognise going on in these numbers? Right. Okay. So simultaneous posts, which is one of the reasons I love chat. You can't do this in like people talking to me in a classroom. You can't do this, but simultaneous in chat is possible. And look at this beautiful symmetry. Jamie has told me all about the right branch, and Miles has told me all about the left side, and they did that simultaneously. What beautiful symmetry. Yeah, Oscar spotted some natural numbers as well. Chat, question for chat here. Are you nice, and why does it seem so nice? Then people, even though with chat, why are you so nice? I think chat is nice. Chat is lightly moderated. That's why your messages take a little moment to appear after you post them. All right, but more theories coming in. Is this live chat? It is a new live chat service. We switch between different live chat services. There's a complicated rules to do with Oxford procurement and buying services. Let's not go there. It is a different service. It annoys everybody every time I switch between the two. The total's in Greek. Oh, total. Seb, tell me about the total. What do you mean by total? I think I know what you mean by total. I mean, like the total's increasing. The total of the whole thing is increasing because there's more and more numbers. But I think you mean something slightly different, right? Number of the left. Nicholas has come back to me about opposites. Number of the left is opposite of the one on the total right, and smaller they get the D. So I think Nicholas has spotted this kind of symmetry thing. That this one over here, like this 3 over 5, it's like the other way up of 5 over 3, and there's a 5 over 2 and a 2 over 5. They're kind of flipped. I think he said swapping or flipped or something. There was something else that someone said as well. Herb said about fractions being reciprocals. Oscar spotted some number. Yeah, I think he said about the sum total of each row is increasing. I do want to talk about the sum of each row. If you want to investigate ahead before I get there, what's the sum total of each row and what's going on there? That's actually the question that I found that I couldn't answer, and I had to do some research to find somebody else telling me the answer. And it's a nice example of something where, well, we'll get there. Right, the right-hand branch is always an improper fraction. Right, okay, Herb spotted whenever you go right, so I'm going to doodle. I know people don't really like it when I doodle on top of diagrams, but I'll undo this in a second. Whenever you go right, you get something that's improper fraction, the top is bigger than the bottom. I guess that's true because a and b are positive numbers, and this is 1 plus a over b. So, but yeah, I think that's true. That's nice. There's an improper fraction, and also, do people call them proper fractions? I suppose they probably do. On the left, a over a plus b is always going to be a proper fraction. So it's less than 1 or bigger than 1. Something like you could use these as coordinates, Miles says. Interesting. We're still running through exam season. Hello. You've got A-level exams in April. Okay. Good luck with your A-level exams. We just keep doing live streams almost all year round, so we're always doing something, more or less. People are giving me the totals. Good stuff. Kai says hi. Hi, Kai. Kai's maybe a UCL offer. Hold it, cool. Yes! Ah. Fibonacci numbers. I love this. So people are adding numbers in chat. They've got 1, 2.5, 5.5, and 11.5. Those are the sums of the rows. The adding gets harder as you go down because there are more and more things, twice as many things to add each row. I think that's a sequence. It's maybe not a sequence that you have seen before. Well, I mean, obviously, of course it's a sequence. It was a stupid thing for me to say, I think that's a sequence, but maybe you can tell me something about this sequence. So this is 5 over 2, and then the next one is 11 over 2, and then this one is 23 over 2 for the sort of sum. 2 lines for that's the sum of the row. Not great notation. Let's put total at the top. Okay, I'd like to come back to that. I think what's going on with these totals? Can we spot any sort of patterns in those? It's not just the totals that I'm interested in. That Fibonacci number was just fantastic. Where are those Fibonacci numbers then? I'm going to highlight on top of the thing and then get rid of this. So is it going alternate left and right? You get this kind of Fibonacci sequence, which is brilliant, isn't it? It's like exploiting the Calkin-Wilf mechanics to store the last 2 numbers as a fraction and to add them using the adding step and store it and add them. It's just so lovely. But yeah, those are the Fibonacci numbers. The Fibonacci numbers are those ones that start 1 and 1 and then add the previous 2. And that's sort of exactly what's happening down this zigzagging branch of the Calkin-Wilf tree. Good spot. I love the Fibonacci numbers, got a lot of time for them. That gives you an idea, by the way, of how fast the numbers are growing. I don't know, if you know how big the Fibonacci numbers are, then it gives you an idea of how quickly the numbers are getting bigger. So that's pretty nice. Cool. Let's just tidy this up a little bit, sorry. Sorry, I saw some comments last time when I was drawing on top of stuff and it all got very, very messy. It's a new season, I'm a new me, and I'm going to try and be more tidy. Multiplying each term in a row produce. Oh, that is cool. That sounds true. That sounds true. Multiplying all the numbers gives you 1. That does sound true. Can I prove that? I think I can see why that's true. So, like in this row, if you multiply them, the numerators are 1, 3, 2, 3, and the denominators are 3, 2, 3, 1. Those are the same thing but backwards, so they have the same product. It's cool, yeah, the product is 1. And I guess product is a sensible thing to think about after we've thought about the sum total. Now what happens if I multiply all these numbers together? Okay, it's always 1, so it's maybe not as exciting. Ah, you're a computer scientist? Seems to be a recursion thing. Yeah, this is one of those heavily recursive things, isn't it? Each child... It's sort of mixed metaphors, but hey, each child depends on the parent, so there's this recursive thing. I guess you might want to think about, if I show you a number in the Calkin-Wilf tree, can you work out where it came from? Should we do that now? Let's do that now, I think. So this is a slightly hard question. I kind of want to keep this box everywhere. How do I do that? Can I group that? Yes, I can. Oh, Myro. Wow. So good. Okay, oops. I've ruined it. Sorry, Myro. I've let you down. Okay. So if I see, let's use some different numbers like C over D in the tree. What's the parent? Where did it come from? Okay. I feel like that's a sort of natural question. I'd like to be able to work forwards and backwards. So we've got the kind of forwards working where we just follow that rule in the pink box. Oh, it's slightly off screen. And maybe I want this backwards thing to work backwards. Jamie, go, what is this fact? The denominator of the totals, if you divide each number in a row, how do you divide each number in a row? Denominator of the square numbers. Oh, I don't know how to divide the numbers. Denominator of the totals if you divide. This is one of the limitations of the chat box, right? You have to explain it in words and then you realise I read it out in a stupid, slow voice. Oh, crikey. I don't know how to divide each of them, sorry. So Nicholas has got a suggestion to my question on the screen. Oh, hello. 1 over 2 over 2 would be 1 over 4. Oh, I see. So if you do division as you go through, if you do loads of division in between, do you get lots of cancellation? I could believe that. I could believe that you get a lot of cancellation if you do some division. Ooh. Ooh, because you're going to end up with, maybe you end up with just a 1 over 3 from the start and a flipped 3 over 1. I could believe that a lot. Sounds very good. And everything else cancels? That could be true. That's quite hard to explain, isn't it? I think I've got there. We've got some suggestions for my C and D problem on the board. And a question from chat, is anybody going to promise? Promise is, I think, part of the application for promise is you do all these maths questions, and I think doing the maths questions is good for you, even if you don't do promise. When I look at them, they remind me a lot of university maths questions, and I've got a feeling that if you go into university maths, you'll enjoy it in the same ways that you enjoy doing promise questions. Division sounds like it do the opposite of cancelling. It would do squaring. Yeah, but you've got, for each one, you've got the one over as well. Oh, yeah, I don't know. I don't know. Maybe I should just hide behind this. I don't know, kind of thing. I sort of believe something could happen with a lot of divisions. Right, cool. We've got answers in chat now for this C and D problem, and I'm going to try and read them out of chat. I like this. So if C is less than D, then the claim is that I should look at C over D minus C as the parent. And I guess that would work because then the child underneath would have the same numerator and the denominator would be the sum, which would be C plus D minus C. Oh, that's D. Good. If C is bigger than D, then there's this sort of slightly different case where it's this. It's got the same, if C is bigger than D, then our fraction is bigger than 1, so it's one of the ones from the right-hand side child. One of these things over here, A plus B over B sort of thing, and then solve some simultaneous equations, rearrange some stuff, and brilliant, it's C minus D over D. Either way though, we can work out what that parent is. We can work out where numbers came from, which is quite good. It says that if I say to you something like, is 8 over 5 in the tree, you can say, well, it depends. First, let me work out something else, and maybe I'll go from there. So, is 8 over 5 in the tree? You might look at that and say, aha, that relies on whether is 3 over 5 in the tree. Because I will C is bigger than D, so I'll look at C minus D. C minus D is 3. 3 over 5. Is 3 over 5 in the tree? Oh, and the answer is yes. There it is. But we could keep working backwards. We could keep working backwards, or we could look at our tree and say, aha, here it is. 3 over 5 is over here. Good. Oscar's put something clever about linked lists in the chat. I say that it's clever without reading it because I know that when I read it, it's going to be too computer sciencey for me. It does sound quite complex. Ooh. Yeah. Each one sort of points to two other things. So you can recursively follow the links. Oh gosh. Data structures, that's what this reminds me of. I think 1.5x cubed is a suggestion. Is that a suggestion for the formula for rotators or something? Maybe? Are there two solutions? Yeah, so COVD could be this thing on the left or it could be the thing on the right. So, but it can't be both of those because one sort of number there is less than one and the other sort of number is bigger than one. So it's only going to be one or the other. It feels like there are two cases to consider, but luckily it's one or the other. It can never satisfy both of those. Here's a great question in chat. Can this tree generate every possible fraction? I think it's the natural question to ask next. After you've worked out that eight of fibers in the tree, maybe the question is something like, is every number in the tree? Good question, which I'm avoiding for a second. What do we think? Oh, every fraction. Let's put rational. Obviously, it would only be the rationals. It's clearly made of rationals. Okay. Oh. Got another person who's on promise questions. Oh, guess that it's a cubic, 1.5x cubed plus. I see, because it's got lots of factors of 1/2. It's actually growing faster than a cubic. That's hard to tell, but it's a good guess to look at 1.5x cubed. Oh, is that third differences? I bet that's third differences. Yeah, so yeah, you might guess a cubic and fit a cubic through those four numbers, but sadly the next one is just huge. This is much larger. Charles thinks the answer is yes, and they've put a proof in chat as well, or sort of one line attempted a proof, which is quite exciting. Numerator and denominator keep decreasing. Reading between the lines, I think Charles means if we do that thing over here on the board, numerator and denominator keep decreasing until eventually you get down to 1, 1, and you say, 1, 1 is in the tree, it's at the top of the tree, and this always works. Broadly speaking, I think that's pretty much correct, and reminds me very closely of an argument I've seen before. I sort of wonder how convincing chat finds it though. I don't know. So it's just up to me. I find the thing that Charles has put in chat very convincing, but that might just be because I've seen a proof before and Charles has correctly reminded me of the thing. There's this odd area about how convincing is your proof, right? Depends who you're trying to convince. So the answer is yes. Maybe I'm biased because I already knew the answer was yes. If we're being really careful with the argument, we might try and think about what it means for those things to decrease as we go down. How these numbers d minus c or c minus d are definitely smaller. We might do some inequalities to check that. And we might be careful that what's really going down, I suppose, is it's not the case that the numerator decreases rather than the denominator. They both end up at 1, so that's slightly weird. It's a slightly sort of reduction. Oh gosh, question in chat. When is that essay competition winners going to be announced? I don't know. I'm going to have to look it up. I think you're referring to the St Edmund Hall essay competition? I really don't know. I think last time it took them quite a while to read all of the things because they got quite a lot of essays submitted. So there's some poor team out there who know is reading a lot of essays. Good luck to anyone who put an essay in, and everyone else. Hey, we get to read their essays. Well, we get to read some of them. They get published at the end as a sort of prize. Good, right, okay, I got sidetracked. In fact, every rational number is in the tree. The sort of most direct proof I know is something like suppose there were some numbers that aren't in the tree, some rational numbers that aren't in the tree. Now, for each of them, work out numerator plus denominator. That's a kind of measure of how complicated your fraction is. You add together the numerator and the denominator. Now, I'd like you to work out the parent of that number. Find the smallest one. Sorry, find the smallest, least complex fraction that's not in the Calkin-Wilf tree. Now, just look at this parent for me. And if you look at this parent using that method, it must have a smaller sum of the parent plus the sum of the denominator plus the numerator. It must be a less complex fraction, which contradicts the idea that you just showed me, the smallest counterexample. That means that you didn't have the smallest counterexample, which in fact means you had no counterexamples at all, because if you had some, you'd be able to show me this smallest one. This is sort of a style of proof I've seen before, which uses proof by contradiction, where you assume maybe these counterexamples exist and you prove that it doesn't work that way. And also is combining this idea of what's the smallest thing. You don't really want to talk about the smallest fraction because you can have very small fractions, but having this kind of complexity measure, like adding together the numerator and denominator. I don't know how much sense I'm making, probably not very much sense, so I'm going to move on in a second. Technically, I think we should look at the sort of complexity of the fraction by adding together. We've got these two numbers that are zipping down to 1. Let's check they both go. What's my favourite type of proof? Do love a proof by contradiction. Some of my students love proof by contradiction even more than me, though. Sometimes I've met students who want to use proof by contradiction even when they could just prove things normally. You can kind of make anything into a proof by contradiction if you say at the start, suppose for contradiction that I can't do this question, and then you do the question, and then you say at the end, therefore, by contradiction, I must be able to do this question. And the kind of dressing at the front and the end about proof by contradiction is not really necessary. But that is my favourite style, I think. Proof by contradiction. Okay, yeah, good, cool. Also an arguing technique, but quite an aggressive arguing technique. Okay, I realised I should put positive in here as well. Thanks for not calling me out on that, chat. See, chat's so nice. Chat could have been jumping on me to say, no, none of the negative fractions are in there. And you'd have been right, none of the negative rational numbers are in there, but it's a communication challenge, isn't it, mathematics? Satisfying end. It feels like you won over somebody. Oh, proof by contradiction. Yeah. It's sort of like imagining your opponent, having an imaginary argument with your opponent. Anyway, right. Proof techniques. What's your favourite proof technique, chat? Interaction, isn't it? Are there other proof techniques that are worth talking about? Yeah, let's be provocative. I claim that there are no other interesting proof techniques. Please could you prove me wrong by contradiction? This is good because even if they do, there's some contradiction to show that there are better ones. Right, good, okay. So I secretly win anyway. Excellent stuff. Follow-up question to the rational numbers question that we just had. Is everything in the tree? The follow-up is kind of to put in here exactly once. So now that we've decided that everything's in the tree, every rational number is in the tree, is everything in there exactly once? I'm going to throw that to chat as well. Nicholas has put some proof in here. The leftist row is getting smaller to infinity, which includes all positive numbers, rational numbers below 1. Ooh, it's not obvious to me you get everything in between. I agree that you're getting small ones and you're getting big ones and you're getting in between things. Could be missing out all the ones where the denominator is the prime 101 or something, right? It could be missing out some small subset that we won't notice. So although it's doing a lot of fractions, and it's doing ones that are small and big and in between, it's awkward that it could be doing something in between. People in chat all like proof by induction, so that's pretty good. So let's follow up which is sort of uniqueness proof. Uniqueness is something that mathematicians try to prove sometimes, that not only is this the solution, it's the only solution. Can't think of any good relatable arguments right now, but hey. Here I'd like to know whether every number, like 8/5, is that in the tree multiple times or just once? And the complexity idea is good again. Oh, someone anonymous at the chat here noticed that some of the numerator and denominator get larger for every child. Pattern can't repeat. Okay, that tells me that underneath 8/5, I never see their like again. I never see 8/5 again underneath 8/5 because I agree the complexity, the sum of the numerator and denominator. I feel like I'm calling that complexity now. Let's put a quick note. Define complexity of A/B as A plus B. And then, oh no, I mean A/B in lowest terms. Right, good. So this argument here in chat at the top at the moment is that the things underneath have higher complexity, sum of numerator and denominator, so you're not going to see 8/5 again. But there's other branches and there's other stuff going on. Like so, 4/3 here has complexity 7, whereas 5/3 has complexity 8. So it's not obvious to me that you can't have it appear once and there's someone else miles away underneath a different number. So that's a bit awkward, isn't it? Practically more and once you'd have clone branches that are a copy of that tree all over again. Yeah. So then after that, it would carry on. If I have two 8/5s, it's a bit annoying because all the stuff underneath is deterministic. It's determined by that 8/5. It'll be like 8/13. Why did I pick such large numbers? 8/13 and 13/5 in both cases. So a whole chunk of tree will be annoyingly the same. And they could happen at sort of different heights and different spaces around. The tree's not quite sorted by complexity. Sorry for the handwriting, that was I wrote it quite quickly and badly. In fact, it is true that each number appears exactly once. I'd like to try and get a reason out of chat, I think. I think we can do this. The key is to think about parents again, and to run some version of this imagining a proof by contradiction or counterexamples. This is a bit tough. So my proof by contradiction, I suppose, would start something like, suppose there's a rational number that appears in the tree twice. Maybe there's loads of these things out there, but 8/5, and we've agreed all their children underneath are going to have the same, they're going to appear twice, at least twice. Choose the least complex one, I think. So maybe 8/5 is the least complex thing that appears twice, let's say, as an example. Choose the least complex example that appears twice. Over to you, what next? Oh, this is collaboration. There's quite a bit of chat lag in the live stream goes from me to the internet to you to the internet. No, wait. And you type, you think and then type, and then the typing goes from the internet to me, and then by the time it gets back to you again, I think we're talking about something else. Parents, yes. Thank you, anonymous person. Does anybody else want to go as well? If you're typing, keep typing. Does that work because of time lag? Maybe that doesn't work because of time lag. No, it works. It works. You see the chat message appear when I... Anyway. Yeah, parents appear twice. Parents appear twice. Brilliant stuff. These must have the same parent number. Which would be, we agreed before, C is bigger than D, so it's 3/5. Ha. Parents appear twice as well. Oh, this looks good. Charles tells me the parent appears twice, and then jumps to tell me that 1/1 appears twice, which, might be able to get a contradiction out of this already, without going all the way back up to 1/1. Find the parent, and the parent, oh, this person wants to go parent to parent as well. Two numbers A and B, and A and B have the same parent, which is not possible. Well, actually, I think you get that kind of straight away, right? You get this 8/5 and 8/5. If that's the least complex number, their parents are both 3/5. Now, each parent has got 2 children. So someone finish this off for me by telling me why can't it be the case Why can't it be the case that these two matching numbers are the two children of 3 over 5? Sorry, I'm writing underneath chat. Why can't it be the case that, you know, because 8 over 5's got the same parent as this other one? Fine, everything's got two children. Why not this? Both the same parent in the same place. I think that's the dichotomy, by the way, that either this supposed least complex example has matching parents in different places, which would be a contradiction because that would be a smaller, less complex example. I should just say less complex, not smaller. That would be a less complex example of a fraction that appears twice. Or it could be the same one if they're the two children of one parent. Yeah. Can't divide by 0. Oh, why are loads of people telling me about 0? Yeah, B is bigger than 0. Oh, yeah. A plus B cannot equal A. Right, good. Okay. Yeah, they don't match. They don't do any of the things in the pink box, right? It doesn't make any sense that these numbers could be. It doesn't make sense that they could be the same. It doesn't make sense that both of them could be bigger than 1, or I suppose both of them less than 1. It doesn't make sense that we divided by A plus B and it was. No, it doesn't make any sense at all. It's just nonsense. Many reasons why not. I sometimes love a proof by contradiction, because sometimes you follow through and the imaginary person you're arguing about says something really stupid, and it just turns out to be easy to say, that definitely doesn't happen, right? Okay, one sibling is proper and the other is not. There you go. Yeah, A and B one must be. I agree with the in this chat message. Maybe we should write that at the end of proof by contradictions. You know, to show. Therefore, both these numbers were divisible by 2, but the fraction was already in lowest common terms. Proof by contradiction. Assuming the other. I like that. I think I can write R in most. Is 0 over 0 in the tree? Why does 0 over 0 help? Its kids are 0 over 0 and 0 over 0. I get it. Yeah, I don't want that. Yeah, okay, not that. Is 0 over 0 in the tree? Definitely not. All of the numbers in the tree are bigger than 0, and they stay bigger than 0 when you add them together. Okay, definitely no zeros. Good call. I get it now. That's why people are telling me about zeros, because they're working backwards. Got it. Definitely not got any zeros. Okay, so recap then. That means that every fraction appears in the tree, and every fraction appears exactly once. And those arguments, those proofs felt quite similar. It looks like, suppose you can find some counterexamples, take the least complex one, now investigate that. It was nonsense. The proof felt quite similar, but heads up is that this tree contains every fraction, every positive fraction, let's put it in here, once each. That's nice. And so this is a way to list all of the fractions, if you like. These people have been adding them together. You're working row by row. And as you're adding them, I guess you're going to look at all of these fractions that you're adding together. And eventually, as you go, you're going to hit every single fraction. Every fraction is involved in one of these row sums. Every fraction appears in one of these rows, and only once. That's quite nice. You could think of this as a way of listing the fractions, like you wanted to count them. A few weeks ago, Zakai came on the show last season to talk about countable and uncountable infinities, and they did a proof in there that the rational number's countable. There's another different proof where you say, hey, make the Calkin-Wilf tree, that's got every fraction in it, and now count your fractions by just going along the rows, counting them as you go. Layer 1 is 1 over 1. Yeah, okay. I might have said something about matching numbers. I might have got too excited and said something about matching numbers that wasn't true. Going back to parents, should we put 0 over 1 or 1 over 0? Should we put 1 over 0 in our tree? Somebody in chat has already said, for the concept of putting 1 over 0 in the tree. What's the parent of that? Where did the 1 come from? I love it. Oh, so people think 1 over 1 has 2 parents. Oh, 1 over 0 and 0 over 1. It's a good thing that that's only in my tree once, right at the top. What would its parents be? 1 over 0. I don't really like that as a number, I think. and 0 over 1. Yeah, okay. I get that. Sure. I might need to put like if they're both bigger than 1, around the proof somewhere in each row, perhaps. Okay. So you've got a big tree full of fractions. Let's talk about this sequence over here. Now, I gave people the challenge about half an hour ago of working out these numbers and trying to find a sequence. I saw at least one person have a go at finding a cubic formula for this. Brilliant stuff. Love the attitude. I think, oh no, people are still on 1 over 0. We got 2 rules on this live stream. They are, don't swear and don't divide by 0. As far as I know, we've only broken each of them once each. We're going to talk about totals now. No dividing by 0, just totals. I gave you the task of trying to add these numbers together, and that went like this, I suppose. We got 5 over 2, 11 over 2, 23 over 2. Maybe you might have spotted those are all odd numbers divided by 2. If I write this one as 3 over 1's equal to 2 over 2, James, not 3 over 2. If I write this one as 2 over 2, then it kind of fits in the pattern, which makes it look nice. I can also, I've written these out as sort of improper fractions, but I could also write them out like this, at which point maybe you can see what's going on slightly more clearly. There's this relationship between the numbers that you can maybe spot. Oh no, people are finding the parents of 1. It's getting out of hand. Do you think 0 over 1 goes to 0 over 1? Is that true? Oh no, I think it might be true. That's brilliant. Right, okay, if we allow this sort of thing, exploring north of the North Pole is... I think there's something weird going on. There's something weird going on if you're allowed to do things like 1 over 0. And I suppose if you're squeamish about 1 over 0, like me, then you could pretend that none of these were fractions at all. They were just... instead of putting a horizontal line between the 2 numbers, I'll write vectors like this, and then you're allowed to do 0 as the lower number, and it's all fine. You can draw them differently, but still keep the fact that you've got 2 numbers, and keep the operation kind of the same. You have that kind of alternative where you could write them out like that, and then you're not dividing by 0. You're just writing down a 0 in a vector shape. Oh, I'm behind on chat. Sorry. Yeah, people are mocking me for the 2. Good. Yeah, numerators. Yeah, people spotted the pattern. Brilliant stuff. It's not quite squares. Miles did this too. Yeah, people are going to try and put them trees backwards and then convince me that things are in the tree twice because they're in their weird mirror universe tree. My tree starts at 1. Calkin-Wilf. Their tree starts at 1. It's not my tree. So maybe you can spot there's a pattern here. This 2 reminds me of this 2. Because this 5 reminds me of this 5, this 11 reminds me of this 11. So I suppose my rule is something like this. I saw it in chat as well. Can I read it out of chat? Sum of each row. Multiply the numerator by 2 plus 1 over 2. Yeah, so multiply the previous thing. If I call these, what's a fancy thing to call these? I could call this sum, S for sum, with a little subscript for which row we're in. Counting by 0, like how we count episodes by 0. Starting from 0, and then I guess my rule down here would be something like the next one, Sn, is equal to 2 times S, the previous one, plus an extra 1 over 2. Then double it up, get rid of this 2, and then add on 1/2. This is in the class of true but not obvious. This pattern continues. It's almost annoying how it continues. You can work out there are 16 fractions in the row below. You can add them all up. You can try to look for patterns and how they all add up, and yeah, it makes 23.5 fits in this pattern of double the previous thing to get 23, add 1/2, 23.5. That's what the next row adds up to. And this is the thing that I wanted to try and prove, and I couldn't. So, in a slightly weird twist, because we've got extra time this week, I'd like to show you what it's like to not be able to prove something and then look it up and research it. We're going to go on a little journey of failing to do a thing, reading somebody else's work, adapting what they've done, realising what the idea was, learning from the mistake. Well, learning from the mistake. I've been told off for counting from 0. Can I count myself as friend 0? I think I'm friend 0. Good, right, okay. Here's how I tried to prove it. That this thing that there's this relationship between the sum of the rows. What I noticed was the denominators repeat. Over here I've got 1 over 4. And over here I've got 3 over 4, and I found that quite exciting because they add up to 1, which is a nice thing to add up to. And over here I've got 4/3 and 5/3, and if I sort of zigzag inwards and sort of spiral inwards like this is quite sort of hypnotic as an idea. I've got this 4 over here, and then I'll be left with something over 2, so it feels like if I add them on the way in, then it will be something and a half. So a whole number plus a half, and I feel like I'm onto something about how to show this 1/2. Don't feel very close to a recursion relation like this, relating it to the previous one, but maybe I could just do this and do the adding and it will just fall out. And then I failed at doing that because it's really complicated trying to explain how this element relates to that one over there. 3 over 4 is so far away, it's so hard to explain. For that you'd have to go up 3 levels and then down 3, but make the opposite decision at the last minute. And the other ones are related in an even more complicated way. That's like make a slightly different decision along the way and you get almost the same numbers. They add to an integer, I promise. This was not a good proof technique. So it's sort of true that I can add together pairs of these fractions, but it's not a very useful truth as far as I can tell. That's not really a thing, right? If I say useful truth, it's not really a thing, but it's how it felt to me. So disaster, right? We've got this nice result. There's something that looks really true, that there's this recurrence relation between the rows of the Calkin-Wilf tree. Probably some nice sum if I can solve that recursion relation, which I think I can do some university maths or something to solve what the answer is for that sequence. Probably some nice formula here, but I can't prove why it's true and I can't work out what's going on. And when you're at school, I always encourage you not to look at the answers, to not go and look it up. Don't look at the thing in the back of the book. Don't read the math solutions before you finish trying the math question. But don't go and look somewhere else. Don't go and look at the answer. But in actual maths research, that's not how it works at all. People have done loads of maths before. You should look at it. It's almost rude not to. If other people out there have done loads and loads of maths. Definitely not the first people to think about the Calkin-Wilf thing. So if I want to know the answer, one thing I can do is go and try and find it. We're going to talk about that. Counting at 0 has ignited the same conversation that it normally does. I think Nicholas has a comment about 0 counting or something. Formula doesn't work for 1 over 1. It doesn't work for... Okay, if you're in this world where 1 over 1 comes from somewhere, it's secretly got some secret parents, you're discovering the hidden ancestry of 1 over 1, then I don't know if my formula works over there. Sort of undiscovered territory north of 1 over 1, but I'm smiling when I talk about it because I think it's fun to explore, but yeah, no warranty for whether the formula continues over there. Cool. So I went and looked up someone's paper for some of the rows of Calkin-Wilf tree is what I looked for. And mathematicians are quite good at putting papers on the web. There are a few good sources of papers. One's called Preprint, which is it's called Archive, A-R-X-I-V, and that's where I found this paper. And this is from Archive. Archive's pretty good. It's where mathematicians put papers that haven't been peer-reviewed or accepted in journals yet, and without the formatting from the journal, but it's how you get their results. See what they're up to as soon as possible. Okay, this paper's from 2018, so maybe I could go and find it in a journal or something, but hey, this is where I found it. People are now arguing about -1. I really like the people who are trying to put negative numbers into the Calkin-Wilf tree. I don't know where they live. They definitely don't turn up below 1/1. Right, here's the challenge of reading a maths paper. This is by a team, first author Sandy Han. I think these mathematicians are at the University of New York. And yeah, working on a variety of different things. Anyway, here's the challenge. So you can look at the abstract, and that gives you a clue about whether you're going to read the right thing. And you find that mathematicians love putting superscripts and subscripts on things, and curly letters. Infinite binary tree sounds about right. Each vertex, left child, okay. It sounds like a variant of the thing we're doing before. And then, to be honest, I stopped reading a bit because it's going a bit confusing. But I've seen Calkin-Wilf over here, so I think I'm onto the right sort of maths. This one this doesn't mean very much to me right now, but mean row value is what I'm looking for, I guess. I suppose mean, like average, means that these people who have found the sum and then divided by 2 to the n to work out 2 to the n plus 1 maybe? Divided by, I'll have to worry about that in a minute, that they've done some dividing to work out that average. And they said it converges, oh gosh, so it gets close to something, does it uniformly, so there's some technical details that you've done. And then, to be honest, I skim read and look through the pictures. Here's the Calkin-Wilf tree, brilliant, good. Happy, we're in the right place. We found this paper is going to have facts about the Calkin-Wilf tree, maybe. There's some stuff going on. I've got a more complicated diagram that I looked at briefly. It's got their U's and V's in. I'm not sure I'm that interested in the U's and V's. My Calkin-Wilf tree doesn't have any U's and V's in it, so I'm going to hope that those aren't too important. There's some stuff going on here, and then over the page they've got this fact that they've got some approximations, U plus log 2, V plus log 2 over U, and I'm getting a bit worried because now it looks really complicated. Then they start telling us about continued fractions, and I get even more scared because I think I can technically remember how continued fractions work, but I didn't really want to do it. I found a main results section. This is pretty good. Oh my goodness. And I've been skim reading, so my chances of understanding that main result is pretty small. We show that for Z in the set, I don't know what that means because I've been skim reading what U and V are, the limit of the A, I think, is probably some sort of average or something. It exists. This whole thing's about averages, right? For this, the mean and monotonic increasing, oh my goodness, okay, it doesn't sound like what I care about. It doesn't sound like a row average fact. Okay, cool, right, main result, good. Skim reading again, and then it gets more and more complicated. And I realised quickly that this paper is now talking about something that I wasn't thinking about. This paper's gone way beyond anything that I was wondering about. It's now proving some inequalities to do with U and V, numbers that they've got, and looks brilliant. Seems to be a lot of stuff going on here, but this is now miles away from where I wanted to be. And even if I plug in, I think U equals 1 and V equals 1, it was an I, great. Oh, it's an index though. Even if I plug in U equals 1 and V equals 1, this is not looking at like what I wanted to find out, which is just about row sums, right? I was hoping that row sums of the Calkin-Wilf tree. Has binomial coefficients in here. Oh, it's all amazing. So there's a lot of maths going on. In fact, the thing that I care about happened way up at the start, and I shouldn't have skimmed past it. Because way up at the start, they're talking about the Calkin-Wilf tree. Whenever they're talking about T11, that's the Calkin-Wilf tree that I know, that I care about, I guess. The one that I've been talking about so far. How do I spot that? I suppose I started reading the start again, and I found in the case where U and V and Z is like their top number, it's the root of the tree, the very first thing, are all equal to 1. Okay, so this is the case I care about. This is the tree, so I now only care about U equals 1, V equals 1, Z equals 1. For me, today, I just care about U equals 1, V equals 1, Z equals 1. Brilliant, okay. So all of that stuff later on, where they think about bounds on U's and V's and inequalities and stuff, maybe that's more complicated. Also, I've now seen up here, when U equals V equals 1 in their abstract, the mean row value, that is what I care about, I guess. Converges to 3 over 2. Okay, well, goodness knows. Maybe that says that they know how the row totals work because they've got this mean value. Okay, feels like I'm going to have to Up at the top of the paper feels like it's very useful to me. It's like it's going to be some of the rows of the Calkin-Wilf tree. Further down the paper feels like it's all U and V and inequalities. Maybe somewhere in between there's this sweet spot where they happen to do the thing that we want. I've seen the Calkin-Wilf tree. So let's go back here, and I've now skimmed to see that kind of in between the scope of this paper and the starting point of this paper, it feels like they should definitely do the thing that we want. And in fact, it's on page, is this page 2? It's on page 2. Here we are. We've now decided that T11, which is the thing, I can see they've got all these UV superscripts upstairs. So T11 is the thing I'm interested in. That's the Calkin-Wilf tree. For whatever reason, it's T11 of 1 is a Calkin-Wilf tree that I'm interested in. Yes, right. Here's a good bit. The proof of the mean value of the vertices is depth n. This is what we're thinking about. Row n is sort of depth n. And proof that the mean value converges to 3 over 2 is not difficult. Okay, good. Can mean a lot of different things from different authors, but hey, only makes one use of the property, one property of the Calkin-Wilf tree. Okay, brilliant. They've given us the main idea of their proof. I love it when people do this, when they say, here's some maths, but don't worry, the only important bit is this. And it's that thing that people spotted early on, the reciprocals are in the Calkin-Wilf tree. If you've got 3 over 5, then somewhere else in that row you've got 5 over 3. Okay, we're now going to read a proposition and a theorem from an actual maths paper on the Maths Club. It's a bit experimental, we're going to have a go at it. They say that they've done this by induction. They've omitted the details. Okay, I'm skipping the proposition. They're saying that the reciprocals exist. If A over B is in, oh my goodness, that row of the Calkin-Wilf tree. So this semicolon n means the row? I guess, sure. Okay, let's assume it does. And the B over A is also in there. Reciprocals. In the same row. Okay. Here's the theorem. Let AN be, and then this is the average. This sum is done over, man, look at this tiny writing underneath here. I think this just means Y in, smaller pen, sorry. Let's get a tiny pen, okay. Y, this symbol means in, and then we agree that all of this stuff means the row n of the Calkin-Wilf tree. So let's just add up all of the elements. This is sum ranging over all of those elements. Add them all up, please. And they've got this sort of limit, okay, fine. I think they're actually going to work out what it is. Proof, even better, they've defined S of n to be the sum. This is a function for just the sum of all those elements, adding up all those elements of y. So I'm going to call rewriting y as A over b and using the definition of the Calkin-Wilf tree and proposition 1 about reciprocals, we see that for n bigger than or equal to 1, 2 times S of n, oh my goodness, okay, is equal to, and then they've got all manner of stuff on the right hand side. So this for me is like big question mark. I don't know what this is. They've done some maybe simplification. This has got the same stuff underneath the sum, so that's good. It's maybe this that I need to understand of how has this sum turned into this sum. And then it's really simplified down into in terms of S of n minus 1. Plus and there's this weird 3 floating around, but that looks like a good way to understand it. That's a recursion relation. And that's a really good recursion relation, which will give us some sort of, like, down here, recursion relation, brilliant stuff, solve it, gives the answer for what the sum is. They care about the averages, I don't really care about the averages, don't really care about this dividing by 2 to the n, I care about this sum. They've got this formula, 3 over 2, 2 to the n minus 1/2. So what I would do next, I think, is check that this gives the numbers that I care about. Check that I've lined everything up, that this is, they're definitely talking about the connection, the Calkin-Wilf tree, and they're definitely talking about row sums, just to sanity check it. That will give me the sequence 3 over 2 times 1, 2, 4, 8, when n is 1, minus 1/2 in each case. So that would be 3 over 2 minus 1 over 2 is 2 over 2, which is number 1. 3 take away 1 is 2.5. Oh, brilliant, I think this is working. 12 over 2 take away 1 over 2 is 11 over 2, and then 24 take away 1 is 23 over 2. Okay, we've seen these numbers. These are the numbers that we had before. So this shows that this team who wrote this paper are trying to find the same thing as us, which is brilliant. Okay, good. We've managed to match everything up. All we need to do is understand, gosh, 2 lines of their paper, and then maybe we'll understand where these row sums are coming from and what's going on. Okay. What do I recognise? So I recognise this a over a plus b and this b over b plus a. Those are children, or they look a bit like children from the Calkin-Wilf tree, right? This would be a child of a over b, and this would be a child of b over a, I guess. They're trying to use this property that a over b and b over a are both there in the previous row, I think. So then what are these other terms? And it took me ages to notice that if I add these things back together again, then these two terms, a over b plus 1, is equal to a plus b over b. I don't know, maybe I'm an idiot or something, but that's the other child from the Calkin-Wilf tree sort of thing. It just took me ages to notice that that's what's going on. Maybe I needed more brackets or something. So what they've listed inside their brackets there is 4 children of a over b and b over a. Okay. Right, I think I understand what they've written down now. They've written down 4 children from a over b and b over a. And why have they done that? What are they doing? What is going on? Why would you write down the 4 children of a over b and b over a? I suppose they've decided that they're going to write the sum of everything in that row being, those are children of a over b and children of b over a. Oh, and there's a factor of 2. This is really complicated in a way. There's this 2. They're adding up. They're looking at all of the elements in the previous row. So all of these a over b's in the previous row, this n minus 1 row. So this says here, previous row. I can tell it's the previous row because they've written n minus 1. And they add up over all of that, add up not just your children, but add up the children of your reciprocal as well. So for a over b in that row, you can add together your kids and the children of the reciprocal b over a. Now that's going to be double counting all of the things in this row, because you'll count the children from this one and from the reciprocal. When I eventually get round to 8 over 5, I've already thought about 5 over 8. 5 over 8, I found its children and 8 over 5's children. When I hit 8 over 5, I'll do the same thing. So this is why there's a 2 on the left-hand side, because there's a bit of double counting going on here. We've got the children of a over b, the children of b over a. Later on, we're going to hit b over a, because it's one of the elements in the previous row as well. And we'll count its children and the children of the reciprocal, the other way around. Oh my goodness. Okay, so I kind of see how this is writing out, in some way, this is something to do with adding together the children, not just of one thing, but of 2 things from the previous row. Cleverly paired them together. Why am I saying cleverly paired them together? Because I can see that it's going to simplify. Haven't worked out why yet, but I can tell it's going to simplify. Over to you, chat. This took me a surprisingly long time to understand. Why is this line the same as this line? Why is this what have they done? I've got a question mark on it. What's happened in between? Have I got anyone with me? Oh my goodness. I've never tried to do anything like this to show you what it's like trying to understand maths. Arguably, it's much harder and more confusing than trying to explain maths. It's to try and explain somebody else's maths and the process of understanding it. But goodness me. What's going on? So this row is really long and complicated. A over a plus b, a over b, 1, b over b plus a, b over a, 1. It's got a nice symmetry, nice rhythm to it as well. 1 plus 1 is 2. Welcome to the Maths Club. But they've got a 3. Somebody in chat is with me, which is great. That took me ages. When I first found this paper, it took me just really was a question mark of like, where does that 3 come from? Who said anything about 3? But it is because a over the sum plus b over the sum. Yeah. They've just added up the terms. Is this good? This is good. Good, right, okay. I think it's making me look much stupider than I looked before. I think I already looked quite stupid, but we're plumbing new depths of me looking like an idiot. Yeah, well done, chat. These terms add up to 1. They've got the same denominator. It's why it was a good idea. It was a clever idea to list the children and the children of the reciprocal. Let's do an example. Zoom out. I've been looking at this bit for too long. They have cleverly realised that they can take the hard task of adding together the numbers, and they can look at these numbers. Now, adding those together is pretty unpleasant. But if you also add together these numbers, then things work really well because, and these are the children of the reciprocal, you always get some numbers that add up to 1, and the other ones are pretty similar to the numbers in the row before. They're pretty similar, they're each 1 more. So you get 1 from the left children adding together, and the right children, well, they're kind of the same as their parents, plus 1 each. So that's where this 3 has come from. 1 from the left children, and then 1 each from each of your right children. And because the parents were reciprocals, everything nicely matches together. Okay, back into the maths, but that's what they've done. They've paired up children, not just with each other, but with the children of the, matching the parents by reciprocals. Okay, what a great idea. Wish I'd thought of it, because now this sum is looking really nice. It's looking like the sum across, these are the actual numbers inside the previous row, right? A over B and B over A were the parents. And so this thing in here, this thing, when you do the sum, you will get, well, not quite the sum of the stuff in the row, you're double counting again, because you're counting, when you hit A over B, the thing inside the brackets includes A over B, it also includes B over A, and later on in the Calkin-Wilf tree, you're going to hit the number B over A, and you'll do it again. So it looks like a list of the parents, actually a list of all the parents twice. I don't know, I quite like it, like keeping track of these factors of 2, but it is hard to explain out loud what's going on, right? One way to say it is that there's 2 terms inside the brackets, the sum's kind of twice as big, as you might have guessed. It's not just the sum over all of x of the x's, but also the sum of the other reciprocals as well. It'd be hard to do the sum of the reciprocals. Luckily, the Calkin-Wilf tree is very, very pretty with reciprocals. Anyway, those 2 terms I've underlined there give us this thing, again with some double counting, and the 3's, this took me ages, but you get a 3 for every parent. We're adding up across all of the parents in the tree, we get a 3 for each parent. And it is just 1 3 for each parent, I think. So, this is 3, this 3 is that 3, and there's 2 to 1 is the number of things in the previous row. That actually took me a long time to understand as well. Reading maths is really slow. Understanding maths is incredibly slow. To understand, oh my goodness, that 3 really is that 3, and the 2 to the n minus 1 is that, and it's nothing else because it's a power of 2 from the previous row. The number of things in the row is powers of 2. Yeah, I think it's 2 to the n minus 1, and not, for example, 2 to the n or 2 to the n minus 2. Oh my goodness. Adding it all up. When the dust settles, the authors of this paper are left with a fantastic recurrence relation. The sum that you're looking for is the previous sum plus 3 times 2 to the n minus 2, which is a beautiful geometric series. You can add those things up, it works out really nicely. Homework, I think, for people who know about geometric progressions. If you know about geometric progressions, do the geometric series. I guess write out what that recursion relation means for what is Sn. It's the previous thing plus some stuff. Hey, but now the previous thing was the previous one before and before and before. Add them all up, they're really pretty. The very first thing is 1. It's just so nice. So it gives this final result. 3 over 2 to the n minus 1/2. Lovely. Good. So they've got this nice answer for what the sum of the rows is. We could go back and understand we had a different recurrence relation. Ours felt different, right? It's not the same as this. And it's another recurrence relation that's also true about this sequence. I think the one we spotted was something like if you double that number and then fiddle around with the last, fiddle around with that. So when you double this, the power of 2 behaves nicely. You double the minus 1/2, you don't get minus 1/2. You need to add on an extra 1/2. So this does satisfy the recurrence relation we had way up at the top of the screen ages ago. It's not obvious why it would do both, but maybe it does. There's maybe something to explore there. When you have a recurrence relation, what's the solution like? I don't think I've got time to solve all of those now. Okay, this gives me some idea that actually maybe now I'm in the mood to look at the rest of the complicated stuff. I'm sort of so pleased. That's so nice, right? It really did just use this idea that A over B and B over A. Maybe I'm in the mood to read the rest of their paper because, of course, they've got this is a more complicated thing about U's and V's. Let me read their rule again. It's more complicated. If you've got the number Z, then you do this rule for how their Calkin-Wilf tree works. Variant of the Calkin-Wilf tree, which is, I guess, fair enough. You know, you're adding different numbers instead of one each time. And their aim is to show, okay, it's a bit tricky to work it out exactly what the row sums are, but you can still get pretty close. You can do some bounds on the row sums. The maths is way too complicated to do now, and I'm saying that with a smile because it's also way too complicated for me. You just saw me struggling to add numbers together to get one. I'm not gonna claim I understand what's going on in the rest of this paper, but I now feel like I'm slightly closer to understanding what they're up to. I mean, I've understood. What have we done? We've maybe we shouldn't have scanned down at all. We've looked at page 1 and page 2 of a 12-page paper. If the authors see this, then I really like your paper. I think it's great, especially the first 2 pages. Good stuff. But yeah, we had this one. Double your previous number and add 1/2. True, not obvious why. And I actually maintain that it's still true. It's not obvious why. We got a different recurrence relation, right? 2 times the previous thing plus 1/2. Their recurrence relation is different. Why is this one true? I mean, it's sort of true because we now know everything about this, right? We now know the answer. But maybe there's a nice reason why it's doubling, and that adds 1/2. I can imagine there being a different argument, a different bit of reasoning that gives that. And I sort of want to go and try and find that. Cool, okay. I want to show you one more paper, I think, because the original Calkin-Wilf paper is pretty cool. I think that paper is really easy to read. So the previous one we just looked at was very modern, did quite a lot. And the original Calkin-Wilf paper is quite fun and short, and I think it's written in quite a nice way. There's a joke in the first sentence. I like that. They say, the rational is accountable. Here's how to construct an enumeration. They're going to describe a sequence, and here's their list of numbers. It's the list from the Calkin-Wilf tree. But they present it as a list first, before they talk about it as a tree. So here's some nice facts about this. I like this idea that they present their list, almost playful, right? They present their list first, and then say some interesting facts about it before even telling you how the list works. They haven't mentioned the tree yet, right? The denominators of each fraction in the numerator of the next one. Okay, fine, I kind of agree. Look, here's some 4s, here's some 3s. I can see you've done that, cool. So you could just make a sequence by keeping track of those numbers. 1, 1, 2, 1, 3, 2, 3, 1, just shift it. That n+1 is a shifting sort of thing. Shifts the sequence along by 1. Okay, nice. So it's kind of a cool sequence. 1, 1, 2, 1, 3, 2, 3, 1, 4, 3, 5, 2, 5, 3, 4, 1, 5, 4, 7. This paper's going well. I haven't got to the end of page 1 and they've got a mysterious sequence that they haven't explained yet. And they actually count something nice, which is brilliant. It is the number of ways of writing the integer n as the sum of powers of 2, each power being used at most twice, one more than the legal limit for binary expansions. I think that's lovely. It is a counting problem, right? How many ways are there to do that? And they've made it sound a little bit like binary, where you make a number out of powers of 2, but with a modification. And supercurricular maths fun is often about taking something you've seen before, but with a small modification. So we could maybe have started the live stream today by just talking about this problem, right? Let's talk about how many ways are there to make a number in binary if you're allowed to use the same power twice, but no more than twice. And that is what their sequence does. It's kind of big claims, right? I suppose they haven't claimed this has got every fraction in it, and also it's doing something nice along the way. They're relatively prime. I don't think we've talked about relatively prime. It means they have no factors in common. All the fractions turn up in reduced form. Lovely. And there's their big claim. Okay. And then they talk about the trio of fractions. The paper is extremely short, and it's all written like that in a kind of nice, quite friendly style. I got this one from the second source of papers. We mentioned arXiv briefly. The second source of paper is just mathematicians' websites. This one is just from one of the authors put it on their website. They've got a proof here. If you would like to see a mathematics paper write-up of the proof that we were talking about before, about parents and everything occurs and nothing happens twice. You can see it looks quite short, but remember maths is very dense, right? It packs a lot of ideas into a very small space. So this might look like a really trivial short paragraph for reading time, but it contains all of those ideas we were talking about earlier. There's a nice recursion relation for how this function works related to how their tree works. And then if you look at page 4, is this a 4-page paper? Yes, it is. Then they proved that it is... Oh, where am I? Somewhere in here they proved that it's that hyperbinary thing about counting, but you can use the powers twice. Really short paper. I'm going to put it in the further reading because it's just on the author's websites, so we can all have a look at it to learn about that recursion series. Are relatively prime and coprime the same thing? I think they are. Willing to be proved wrong, especially by chat. I would use those words interchangeably. Are there any other maths papers I recommend? Gosh, that's a really hard question. I was pleasantly surprised to find that this one is a paper that I would recommend. I think I would. It says, so warning, it says stuff like relatively prime, just freely, without explaining what that means. So you might need Google search open at the same time, just to check the definitions of some things. But I think this paper is quite kind of accessible and fun. I don't know a lot of papers that are accessible and fun. Most papers I read are a little bit more like this. I mean that in a nice way, right? That here, the amount of things you would Google along the way is quite hard because you would need to think about continued fractions all the way through. I'll keep an eye out going forward. Have I recommended any papers before? Is this a first? Yeah, I think this is a first for Maths Club. Season 6, we're kicking off by recommending an actual academic maths paper that I just think is kind of fun. Brilliant, right, good. I want to do some extensions. Extensions to extensions. We've seen one where you tweak to put U's and V's in, thanks to that first team from New York. There are other sorts of tree you can do. I wanted to talk about the, really quickly. This is a nice thing about going to 5:30. I've got 5 minutes for extra stuff. If you want to ask me any questions about what we've done today, then you can have a go in chat. So it's two mathematicians, Moritz Stern and Akil Brucker. They have a tree as well. You'll like this one, involves dividing by 0. Moritz Stern, mathematician. Akil Brucker, excitingly, a clockmaker. A clockmaker who needed to make some gears. And gears are about ratios, fractions, they're very important. I don't actually understand clocks. Please don't ask me to explain clocks. Their tree works like this. First, you build some walls for the garden. The walls for the garden look like this. You can bunny quote marks if you like, or write them as vectors or something if you're scared about dividing by 0. We have 2 rules on live stream, don't divide by 0. And then start putting numbers halfway in between any existing numbers, including those walls. There's a rule for these that I'll explain in a second, but I'm going to write down a few things first so we've got some examples. Looks like the Calkin-Wilf tree so far, right? It is different. These numbers appear in order, which is nice, I suppose. The thing you do to build this tree, and it is a tree, each thing's got 2 children, but I think I'm going to lay it out like this first, is you find, on the number line you find the things that were already in the tree, or the walls. So you look at the things you'd already written down on the number line. I'm trying to draw them left to right in order. So I'm looking at the things that I already had, look at the pair, and write down a number that's in between where you add together the numerators and add together the denominators. You know, like how you might have hoped that adding fractions together would work like this, where you just add together the numerators and the denominators. You know, if you really remember back to before you knew how to add together fractions. I think I'm doing this right. Yeah, good. Okay. If you do this, so just adding together, the notation is always not helpful, right? UV, the thing underneath would be x plus u, y plus v. But it's kind of more obvious if you draw it out and have the numbers in between. So in between, add together the numerators, add together the denominators, you get these new numbers, and they lie in between. Have I done that right? I've not done that right, that's a 3. It went wrong as soon as I started explaining it. Mathematical gardeners, a subgenre, brilliant stuff. Herb, also sort of gardening word. Anyway, good. I can't believe that I added together 1 and 2 incorrectly. That's a new low. Thanks, chat, for not having time to call me out on that. As you do this, you get different rules along the way. We're adding numerators and adding denominators. You get the same numbers as the Calkin-Wilf tree, but in a different order. Now, these people came before Calkin and Wilf, and they did things with this tree, but Calkin and Wilf managed to do different things with their tree and defined in a different way and joined up in a slightly different rule. So I think it's fair that Calkin and Wilf get a tree too, even though it contains sort of the same numbers. And of course it's not obvious why it contains the same numbers. And I don't just mean right. Overall they both contain all the numbers, spoilers, all the positive fractions. But the generation rules are quite different here. So this 1/0 on the right is there so that along this side, you've always got something to the right hand side, and you keep adding together the numerators and the denominators, and you get the whole numbers over here. So we can play this game if you like. What's going on in this one? Can we find the Fibonacci numbers? Yeah, probably somewhere in there. There are some Fibonacci numbers. Here the Fibonacci numbers nicely converge because they're in about the right places. They converge to 1 over the golden ratio or something along the. Anyway, it's just quite nice. Fibonacci numbers and golden ratio. Maybe we should do some sequences at some point. Should we do some sequences? Do people know the formula for Fibonacci numbers? Actually, don't tell me that. Don't tell me that. Maybe you know a formula for Fibonacci numbers. If you know the formula for Fibonacci numbers, that's fine. Don't type it in chat. It's complicated. If you don't know the formula for the Fibonacci numbers, you might like to think about that. It's quite complicated. I just told people not to type it because it's hard. But you might like to think about that. That's not homework. That's just a suggestion. And so at some point, maybe I'll explain continued fractions, or maybe I'll get a student on to explain continued fractions, because they're fun. If you already know about continued fractions, please convert all of the things on the screen to continued fractions, and then explain what's going on, because it's not obvious, even if you know about continued fractions. Right, I'm getting up to 6:30, which I think I said was the end time. Yeah, there's some suggestions for future stuff here, which we'll see. My plan is to get more students on. The students this term have got exams, so after a while it gets too close to their exams, and also they're doing a lot of revision and getting ready for exams with respect to that. I know that you've got exams maybe as well. Maybe you need a break, and you could be watching these outside of revision time, possibly at double speed. Right. Oh, areas means doubling Fibonacci patterns in numbers in plants. I've heard about this, but I've never really understood it. I thought when someone tried to show us on a pineapple, or was it a pine cone, or little leaves, Fibonacci. I don't really get it. Quite like that. Cool. Herb says good luck to the students, and I will pass that on. I'm hoping to have some students on in between exam revision. Quite often at the start of term, I'm not organised to get students on for the first one, the 0th one. So that's why you've got just me. Calkin-Wilf, good, right. Fun fact, I was going to maybe write a maths question about this, but decided there was everything I wanted to ask about it was too hard. So I guess here we are on Math Club, leftovers. Run through a 2022 Matt. Yeah, there's going to be an entire episode of the Matt live stream on it. If you go to that website, you can see a rough schedule. planned of when we're going to talk about what. At some point, we're going to make one of those really long videos where we talk through all of the solutions. So we've got a pre-recorded video planned, and we've got a live stream planned about Map 22. At the moment, it's got neither of those things. It's got like a 10-minute video solution, and it's got a PDF of some work solutions. But yeah, more 2022 stuff coming as well. Tomorrow, somebody's doing a Sudoku contest. Good luck with your Sudoku contest. And I hope everyone else has a nice evening and a nice week as well. Right, the numbers have got complicated because we're now doing an hour and a half live stream. I will see you in 166 and a half hours. It's not a good sign off. It's just not a good sign off. I'll see you in 166 and a half hours for another episode of the Oxford Online Maths Club. Bye everyone, have a good evening.